Behind the frosted glass of industrial complexes, where flour dust hangs in the air like morning mist and machines hum with mechanical precision, lies one of humanity's most consumed foods being born every single second. You've eaten them countless times. Slurped them from bowls, twirled them on forks, watched them steam in your kitchen. But have you ever stopped to wonder what noodles are truly made of? Not just the ingredients listed on a package, but the real story behind those golden strands that feed billions. Most people believe noodles are simple. Flour and water, perhaps an egg. A grandmother's recipe passed down through generations. But step inside a modern noodle factory, and you'll discover something far more fascinating than tradition. You'll find a world where ancient culinary secrets collide with cutting-edge engineering, where chemistry dances with craftsmanship, and where a simple strand of dough becomes a triumph of food science. The truth is, creating the perfect noodle is one of the most complex manufacturing challenges in the food industry, requiring precision measured in milliseconds and temperatures calibrated to fractions of a degree. What you're about to discover will change how you see every bowl of noodles for the rest of your life. From the wheat fields where it all begins to the hermetically sealed packaging that keeps them fresh for months, the journey of a noodle is a story of transformation. It's a tale of how raw grain becomes silken texture, how moisture content determines destiny, and how a factory can produce 40,000 pounds of noodles every single hour while maintaining quality that would make traditional pasta makers weep with envy. The hidden world of noodle manufacturing isn't just about food production. It's about the intersection of agriculture, chemistry, mechanical engineering, and culinary art, all working in perfect harmony to create something so familiar we take it for granted. Let's pull back the curtain and step inside. Here's something that will surprise you. Not all noodles are created equal, and the difference has nothing to do with brand names or price points. The secret lies in something called the protein matrix, a microscopic network of gluten strands that determines whether your noodles will be chewy, springy, firm, or disappointingly mushy. The wheat used in premium noodle production contains between 12 and 14% protein, carefully selected from specific growing regions where soil composition and climate create the perfect conditions. Japanese ramen manufacturers prefer hard red spring wheat from Canada and the northern United States, while Chinese alkaline noodle producers seek Australian hard wheat varieties. This isn't random preference. It's food science at its most sophisticated. Consider this remarkable fact. A single grain of wheat contains over 20,000 individual components, including starches, proteins, lipids, minerals, and countless enzymes. During the milling process, these components are separated with surgical precision, creating dozens of different flour grades. The endosperm, which makes up about 83% of the kernel, becomes the white flour most people recognize. But within that endosperm are subtle variations in particle size, protein content, and ash levels that can make or break a noodle's texture. Master noodle makers can identify flour quality by touch alone, rubbing it between their fingers to assess particle fineness and moisture content, a skill that takes decades to develop. The water used in noodle production is equally crucial, and this is where things get truly fascinating. Tap water won't cut it in professional manufacturing. Industrial noodle factories use water that's been triple filtered, deionized, and adjusted to specific mineral compositions. The pH level must hover between 6 and 7, and the hardness, measured in parts per million of calcium carbonate, needs precise calibration. Japanese ramen noodles use alkaline water, infused with potassium carbonate and sodium carbonate, which gives them that distinctive yellow color and springy texture. The alkalinity isn't just for show. It fundamentally changes how gluten proteins bond, creating a chewier, more resilient noodle that can withstand boiling water without turning to mush. Here's where it gets even more interesting. Temperature control during mixing is so critical that factories install massive refrigeration systems just to keep the mixing rooms cool. When flour and water combine, friction generates heat, and even a few degrees of temperature variation can alter the gluten development. Premium manufacturers maintain mixing room temperatures between 64 and 68 degrees Fahrenheit, controlling humidity levels simultaneously. The mixing process itself is a carefully choreographed ballet of speed and timing. Too fast, and you develop excessive gluten, creating tough, rubbery noodles. Too slow, and the gluten network remains weak, producing noodles that fall apart during cooking. But here's something most people never learn. Salt isn't just for flavor in noodle production. It's a crucial structural component that strengthens the gluten network and controls enzymatic activity. Industrial noodle makers add salt at a concentration between 1 and 3% of flour weight, dissolved completely in water before mixing to ensure even distribution. The salt ions interfere with the electrostatic repulsion between gluten proteins, allowing them to bond more closely and create a tighter, more resilient structure. This is why restaurant ramen tastes different from instant noodles. The salt concentration, combined with alkaline water, creates a texture that home cooks struggle to replicate. Now, let's talk about something that sounds almost magical: resting time. After the initial mixing, the dough must rest, allowing the flour to fully hydrate and the gluten network to relax. In traditional pasta making, this might take 30 minutes. In industrial noodle production, engineers have optimized this process using climate-controlled resting chambers where temperature and humidity are precisely maintained. The dough sits in these chambers for exactly 15 to 45 minutes, depending on the noodle variety being produced. During this time, microscopic changes occur within the dough structure. Water molecules migrate, enzymes work to break down starches, and the gluten network reorganizes itself into the ideal configuration for rolling. If you're enjoying these behind-the-scenes insights, make sure to subscribe to the channel and hit that like button. There's so much more to discover about the hidden world of everyday manufacturing. Here's a mind-blowing statistic. A modern industrial noodle factory can produce enough noodles in a single day to create a strand that would wrap around Earth's equator twice. We're talking about production rates that exceed 5 tons per hour in large facilities, with quality control so stringent that defective noodles are detected and removed faster than a human eye can perceive. The scale of noodle manufacturing is almost incomprehensible, yet the attention to detail remains obsessive. Every batch is tested for moisture content, cooking time, texture after boiling, and color consistency. Laboratories within these factories run dozens of tests daily, ensuring each package meets exact specifications. The innovation in noodle manufacturing extends to ingredient science as well. While traditional noodles contain only flour, water, and salt, modern varieties incorporate a fascinating array of additives that enhance shelf life, texture, and nutritional value. Riboflavin gives instant ramen its distinctive yellow color while adding vitamin B2. Guar gum and xanthan gum, derived from natural sources, improve texture and prevent the noodles from becoming sticky during cooking. Some manufacturers add wheat gluten directly to the dough, boosting protein content and creating an even stronger structure. These aren't cheap shortcuts. They're carefully researched improvements that allow noodles to remain fresh for months without refrigeration, a crucial factor in feeding populations worldwide. Consider the global impact. Over 100 billion servings of instant noodles are consumed annually worldwide. That's roughly 14 servings for every person on Earth. The invention of instant noodles by Momofuku Ando in 1958 revolutionized food manufacturing and created an entirely new category of convenience food. His innovation wasn't just about speed. It was about creating a product that could withstand storage, retain flavor, and cook perfectly every single time. The process he developed, involving flash frying at precisely 160 degrees Celsius, removed moisture while creating tiny air pockets throughout the noodle structure, allowing rapid rehydration during cooking. Here's something that will change how you think about instant noodles. Those wavy, compressed blocks aren't random. The wave pattern is carefully engineered to allow hot water to circulate evenly during cooking, ensuring uniform hydration. The compression prevents breakage during shipping while maintaining structural integrity. Even the positioning of seasoning packets within the package is calculated to protect the noodles from crushing. Every aspect of instant noodle design represents decades of research into packaging science, food chemistry, and consumer behavior. The environmental considerations in modern noodle manufacturing have become increasingly sophisticated. Water recycling systems capture and purify the water used in cooling and steam generation, reducing consumption by up to 70%. Heat recovery systems capture the thermal energy from drying ovens and redirect it to other processes, dramatically improving energy efficiency. Some factories have achieved zero-waste certification, converting all production scraps into animal feed or agricultural fertilizer. The industry has recognized that sustainability isn't just ethically important, it's economically essential for long-term viability. Let's explore something truly surprising about noodle varieties. There are over 1,200 distinct types of noodles produced commercially worldwide, each with unique characteristics determined by ingredient ratios, processing methods, and cultural traditions. Italian pasta differs fundamentally from Japanese udon, which bears no resemblance to Chinese lo mein or Korean naengmyeon. The differences aren't superficial. They reflect profound variations in wheat varieties, water chemistry, drying temperatures, and cultural preferences for texture and flavor. A factory that produces multiple noodle types must maintain separate production lines, each calibrated precisely for its specific product, making the manufacturing process exponentially more complex. The quality control measures in premium noodle factories approach pharmaceutical standards. Imaging systems photograph every noodle strand at high resolution, analyzing color uniformity, thickness consistency, and surface texture. Defective noodles are ejected by compressed air jets with millisecond precision, removed before they reach packaging. Metal detectors scan for any trace of foreign objects, while X-ray machines verify that seasoning packets contain the correct contents. The reject rate in top-tier facilities is measured in parts per million, an astonishing achievement considering the production volumes involved. Here's a fascinating historical detail. Noodles may be over 4,000 years old, making them one of humanity's oldest prepared foods. Archaeological evidence from northwestern China revealed a sealed bowl containing remarkably preserved noodles made from millet, dating back approximately 4,000 years. This discovery rewrote food history and demonstrated that noodle-making techniques existed far earlier than previously believed. The techniques have evolved dramatically, but the fundamental principle remains unchanged, transforming grain and water into something greater than the sum of its parts. Now, let's step into the factory itself and discover how these miraculous strands are actually made. The journey begins long before wheat enters the factory, in agricultural regions specifically chosen for their climate and soil composition. Premium noodle manufacturers contract directly with farmers, specifying exact wheat varieties and growing conditions. The wheat is harvested at precisely the right moisture content, typically between 12 and 14%, then transported in climate-controlled containers to prevent spoilage. Upon arrival at the factory, the wheat undergoes rigorous testing for protein content, moisture level, and contamination. Only wheat that meets exacting standards proceeds to the milling facility. Modern flour mills are technological marvels, using a process called gradual reduction to separate wheat kernels into dozens of different products. The wheat first passes through cleaning machines that remove dust, chaff, and foreign materials using screens, magnets, and air currents. Then it enters the milling system, where it's cracked open by corrugated steel rollers, separating the bran, germ, and endosperm. The endosperm, which will become flour, passes through a series of progressively finer rollers, each stage producing a specific particle size. The finest grades, with particle sizes around 50 microns, are reserved for premium noodles. The entire milling process generates almost no waste, with bran and germ sold for animal feed and health food products. The flour arrives in the noodle factory through pneumatic conveying systems, traveling through sealed pipes from storage silos to weighing stations. These systems prevent contamination while allowing rapid, precise flour delivery. At the weighing station, computerized scales measure exact quantities, typically working in batches of several hundred kilograms. The accuracy is remarkable, with variations kept within plus or minus 50 grams even for batches weighing half a ton. This precision ensures absolute consistency across thousands of production runs. Simultaneously, water preparation begins in a dedicated treatment facility within the factory. Municipal water enters filtration systems that remove chlorine, sediment, and organic compounds through activated carbon filters and reverse osmosis membranes. 4 alkaline noodles, potassium carbonate and sodium carbonate, are added to achieve pH levels between 9 and 11. The water temperature is adjusted using heat exchangers, bringing it to exactly the temperature specified in the recipe, usually between 55 and 70 degrees Fahrenheit depending on the season and ambient conditions. Salt and any additional ingredients dissolve completely in this prepared water before mixing begins. The mixing stage represents the critical first transformation, where disparate ingredients become a unified dough. Industrial mixers are massive machines, capable of handling 500 to 1,000 kilograms of ingredients per batch. Inside these mixers, specially designed blades rotate at carefully calculated speeds, typically between 20 and 40 revolutions per minute. The mixing time varies by recipe but generally lasts 8 to 12 minutes. Engineers monitor the process through transparent inspection ports, watching for the moment when the mixture transitions from a shaggy, uneven mass to a cohesive dough with uniform texture and color. Sensors measure torque and resistance, providing real-time feedback about gluten development. After mixing, the dough moves to the resting chamber, a climate-controlled room where temperature hovers around 70 degrees Fahrenheit and humidity remains at 75 to 80%. The dough rests in large containers, covered to prevent surface drying. During this crucial period, flour particles absorb water completely, and the gluten network relaxes, making the dough easier to roll. Enzymes naturally present in flour begin breaking down complex starches into simpler sugars, contributing to flavor development. The resting time is never rushed. Premium manufacturers allow up to 45 minutes, understanding that patience at this stage determines final product quality. The rolling process begins with compound rollers, massive machines with steel cylinders weighing several tons each. The rested dough is fed between two rollers set far apart, perhaps 6 or 7 centimeters. The dough emerges as a thick, rough sheet. It then passes through subsequent roller pairs, each set closer together than the previous, progressively reducing thickness while developing the gluten network. This gradual reduction is essential. Forcing dough through rollers set too close together would tear the gluten strands, creating weak noodles. Factories typically use 7 to 11 rolling stages, with the final thickness ranging from 1 to 3 millimeters depending on the noodle variety being produced. Between rolling stages, the dough sheet passes over slitting rollers, specialized cylinders with precisely machined grooves that cut the sheet into individual noodle strands. The spacing and depth of these grooves determine noodle width and thickness. Manufacturing facilities maintain extensive inventories of slitting rollers, each designed for specific noodle types. Changing from one noodle variety to another requires swapping rollers, a process that can take several hours and demands careful alignment to ensure cutting precision. The tolerances are extraordinary, with groove dimensions held to within 25 microns, about 1/4 the thickness of a human hair. For instant noodles, the next stage is steaming, where the cut noodles pass through a pressurized steam chamber. The steam gelatinizes the starch on the noodle surface, creating a partially cooked texture that will later allow rapid rehydration. The steaming time is remarkably brief, typically 90 seconds to 3 minutes at temperatures around 100 degrees Celsius. Precise control is essential. Understeaming leaves raw flour taste, while oversteaming can cause the noodles to become mushy. Factories use sophisticated pressure and temperature controls, monitoring conditions continuously and adjusting in real time to maintain optimal results. Following steaming, instant noodles undergo either frying or air drying, the two primary methods for moisture removal and preservation. In the frying process, noodles are immersed in palm oil heated to between 140 and 160 degrees Celsius for approximately 1 to 2 minutes. The intense heat causes water within the noodles to vaporize rapidly, creating the characteristic porous structure. The oil temperature must remain constant, as variations affect both texture and shelf life. Modern fryers use computerized controls and heat recovery systems, maintaining precise temperatures while minimizing energy consumption. The fried noodles emerge with moisture content reduced from around 35% to less than 3%, the level required for long-term storage stability. Air drying, the alternative method, takes much longer but produces noodles with lower fat content. The noodles move through drying tunnels where hot air, typically between 70 and 90 degrees Celsius, flows across them for 30 to 60 minutes. The process must be carefully controlled to prevent surface cracking, which occurs when the exterior dries too quickly relative to the interior. Multi-stage drying systems gradually reduce moisture, with temperature and airflow adjusted at each stage. The result is noodles with moisture content similar to fried varieties but with a different texture and longer shelf life potential. Fresh noodles destined for immediate consumption or refrigerated storage skip the drying stage entirely. Instead, they're cooled rapidly after cutting, often using refrigerated air or water spray systems. The cooling halts enzymatic activity and bacterial growth, preserving freshness. These noodles are then packaged immediately in modified atmosphere packaging, where the air inside the package is replaced with nitrogen or carbon dioxide to extend shelf life. Fresh noodles can remain viable for 3 to 4 weeks under refrigeration, though texture gradually changes as starch retrogradation occurs. The packaging stage represents the final critical step where product protection meets marketing appeal. Modern packaging lines operate at breathtaking speeds, handling hundreds of packages per minute. The noodles are weighed by computerized scales that adjust portions to within a few grams of target weight, then deposited into packaging films. 4 instant noodles, seasoning packets, dried vegetables, and oil sachets are added by separate mechanisms, each time to arrive at precisely the correct position. The packages are sealed using heat or ultrasonic welding, creating airtight barriers that protect against moisture, oxygen, and light. Quality control throughout the packaging process involves multiple verification steps. Vision systems inspect package seals for defects, while metal detectors screen for any contamination. Weight checkers ensure each package contains the correct amount of product, automatically rejecting underweight or overweight units. Batch codes are printed on each package, allowing complete traceability back to specific production runs. If a quality issue is discovered, manufacturers can identify and recall the exact batches affected, a crucial capability for consumer safety and regulatory compliance. The finished packages are collected into cases, stacked on pallets, and moved to warehouse facilities where they await distribution. Climate control in these warehouses maintains optimal storage conditions, preventing quality degradation before the products reach consumers. So now you understand the incredible complexity hidden within something as simple as a bowl of noodles. From wheat selection to final packaging, every step represents decades of refinement and engineering innovation. The next time you prepare noodles, whether boiling fresh pasta or adding hot water to an instant cup, you'll appreciate the remarkable journey those strands have taken to reach your table. But here's the thing, noodles are just the beginning. The world of food manufacturing is filled with equally fascinating processes, each with its own secrets and innovations. Speaking of which, have you ever wondered how a tiny jasmine flower becomes a bottle of luxury perfume? The process is absolutely mind-blowing, involving technology that seems almost magical. That video just appeared on your screen, and I guarantee it will change how you think about fragrance forever. The engineering challenges in perfume manufacturing make noodle production look simple by comparison. Before you go, I'd love to hear from you in the comments below. What surprised you most about noodle manufacturing? Was it the precision engineering, the chemical transformations, or maybe the global scale of production? Drop your thoughts below, and if you enjoyed this deep dive into industrial processes, make sure you're subscribed so you don't miss future episodes. We are peeling back the curtain on how everyday products are really made, revealing the hidden genius behind things you use every single day. Until next time, stay curious.